All right, in this question, we are given a matrix A with components 2, 1, C, and 6, where C is some unknown real number. And in each part of the question, we are told some fact that is true about A, and our job is to figure out the value of C that makes that fact true, and also the corresponding eigenvalues of the matrix. Okay, so in part A, we're told that A is not invertible. So what this must mean is that the rank of A is less than 2. There are lots of implications of this fact, but the most directly useful one for us is that the columns of C must be scalar multiples of each other. Okay? And so since this column is 1, 6, and this first column has a 2 in the first component while this has a 1, if we make C equal to 12, well, then this second column would be double the first column, so it must be that C is equal to 12 in this case. That would lead to a matrix that looks like this. Now, what are the corresponding eigenvalues? Well, one fact that you need to remember is that if a matrix is not invertible, then for sure one of its eigenvalues is equal to 0. So it has a lambda of 0. What is the other eigenvalue? Well, another fact that you need to know is that the sum of the eigenvalues of any matrix is equal to its trace, which is the same as the sum of its diagonal entries. So what we also know is that its two eigenvalues must add up to whatever 2 plus 6 is, which is 8. And since one of the eigenvalues is 0, the other eigenvalue must be 8. So now these two eigenvalues add up to the diagonal. And then the other one of these checks to be familiar with is that the eigenvalues must multiply to whatever the determinant of this matrix is. The determinant of this matrix is 2 times 6 minus 1 times 12, which is 0. And indeed, that is still true, right? The determinant being 0 is what tells us the matrix is not invertible, which, as I said earlier, tells us 0 is an eigenvalue. Okay, now the question tells us to sort the eigenvalues in decreasing order. So if I were answering this question on the exam, I would say lambda 1 is 8 and lambda 2 is 0. But in general, that's how we would go about this. Okay, cool. Now in the next part, we are told that A's characteristic polynomial is the polynomial lambda squared minus 8 lambda plus 7. Now, this polynomial factors nicely into lambda minus 1 times lambda minus 7. And what this tells us right here is what the two eigenvalues of A are. They are 1 and 7. So knowing that we need to sort them in decreasing order, I'll say lambda 1 is 7 and lambda 2 is 1. Now the question is, what value of C makes this happen? Well, let's think about the two rules I just mentioned before. The two rules were that the eigenvalues must sum to the trace. Here the trace is 8, and 7 plus 1 is 8, and so that's good. But they also must multiply to the determinant. Now the determinant of this matrix, when we don't know the value of C, is an expression involving C. So we can solve for that here. It would be 12 minus C. But what I'm saying is that this determinant must be equal to the product of our two eigenvalues, 7 and 1. So now we just have an expression that we can solve for C. 12 minus C has to be 7, which tells us C must be 5. So if A's characteristic polynomial is lambda squared minus 8 lambda plus 7, well then C is 5, and these are its two eigenvalues, 7 and 1. Finally, we are told that A is not diagonalizable. What does this mean? Well, it means that A does not have a total of two linearly independent eigenvectors. Another way of interpreting this is that A has an eigenvalue whose algebraic multiplicity is greater than its corresponding geometric multiplicity. The way we talked about this in lecture is that there's at least one eigenvalue that didn't live up to its full potential. Its algebraic multiplicity said, hey, this eigenvalue is repeated 5 times, but the dimension of the corresponding eigenspace was less than 5. 5 was just a made-up number here. Here, the maximum dimension of an eigenspace could be 2 because the columns and rows of this matrix live in R2. But you get the idea. What we're being told here is that there is an eigenvalue that has a geometric multiplicity less than its algebraic multiplicity. But what that really means, since we're looking at a 2 by 2 matrix, is that A must have a repeated eigenvalue. Okay, it only has 2 eigenvalues total, and it's telling us those both must be the same. But whatever they are, call them lambda and lambda. Now, I'm not using different subscripts here because they're the same lambda. They must still satisfy the same properties I mentioned before, in that they must add up to the trace, which is 8, and they must multiply to the determinant. So if lambda plus lambda is 8, well then it's no surprise that lambda is 4. So this matrix has the repeated eigenvalue of 4, and if I were answering this question on the exam, I would fill in both of the lambda boxes with 4. Then the question is, what must C be? Well, now we use the fact that the determinant of A, which, like we saw earlier, is 12 minus C, is equal to the product of the eigenvalues, which is 4 times 4, which is 16. That tells you C must be negative 4. Okay, so if we plug in C equals negative 4 here, then this matrix is not diagonalizable. Otherwise, it is diagonalizable. If you find its eigenvalues, they will be 2 distinct numbers they'll just be 2 distinct numbers. Okay, because if they could have been 2 other distinct numbers, well, then they would have had to also satisfy number plus itself equals 8, but there's only one solution to 2 lambda equals 8, and that's lambda equals 4. So this is the only case in which A is not diagonalizable. Okay, that's this question. So after I originally recorded this video, a student came to me in office hours and said, why didn't you verify that the matrix actually isn't diagonalizable when C is equal to negative 4? So first, let's do that, but then let me talk about why you didn't actually need to verify that it truly isn't diagonalizable with this value of C. But first, like I said, let's actually do it. So the conclusion was that C equals negative 4 makes this matrix not diagonalizable. Let's verify that. Okay, cool. How do we verify that it's not diagonalizable? Suppose we were just given this matrix from scratch. We know it's going to have 2 eigenvalues of 4. So the eigenvalue of 4 is going to have an arithmetic multiplicity of 2. The question is, what is 4's geometric multiplicity? To find that out, we need to look at the set of all eigenvectors for the eigenvalue of 4. So one way to do that is to consider the matrix A minus 4i, which equates to subtracting 4 off the diagonal entries. That's going to give me a negative 2 in the top left. These entries stay the same. And in the bottom right, I get a 2. The null space of A minus 4i is the set of all vectors that are eigenvectors of A with eigenvalue 4. Okay, so the question is, what is the dimension of the null space of A minus 4i? Well, A minus 4i is a rank 1 matrix. This column times negative 2 gives me this column. So the rank of A minus 4i is 1, but the rank nullity theorem tells me the dimension of the null space of A minus 4i is the number of columns of A minus 4i minus its rank, which is 2 minus 1, which is also 1. That is, the dimension of the null space of A minus 4i is equal to 2 minus the rank of A minus 4i, which is 2 minus 1, which is 1. But the dimension of the null space of A minus lambda I is just the geometric multiplicity of the eigenvalue 4. That is how we define the geometric multiplicity of an eigenvalue. It's the dimension of the null space of A minus that lambda times I. But since the dimension of the null space of A minus 4i is 1, it means I can only find one linearly independent eigenvector for the eigenvalue of 4. That linearly independent eigenvector points in the direction of the vector 1, 2. Right? Because if I take 1 of this column plus 2 of this column, I get back the 0 vector. That's in the null space of A minus 4i. So if I take a vector 1, 2 and multiply A by that, I'm going to get back 4 of my original vector. So I get 2 plus 2, that gives me 4. And here I'm going to get negative 4 plus 12, which is 8, which is indeed 4 times 1, 2. The issue is that there isn't a vector that is linearly independent from 1, 2 that I could also do this with, right? Any other vector that if I multiply it by a, I get back 4 times itself is just going to be a scalar multiple of 1, 2. So since the dimension of the eigenspace for lambda equals 4 is just 1, the geometric multiplicity of 4 is 1. That is less than 2. That means this matrix does not have n, or 2, linearly independent eigenvectors, so this matrix is not diagonalizable. Now from the perspective of the question, why was this step not necessary? It's because we didn't give you the option to state that the provided statement in the question, here a being not diagonalizable, was impossible to satisfy, or it's impossible to tell whether it's satisfied, or there are multiple possible answers. Because we said find a value of c that makes a not diagonalizable, this had to be the answer to the question. C equals -4. Okay.